And you thought the SI system of measurement was complicated. Well, really, it's nothing more than this. There are 7 base units. Be sure you know these, of course, and their abbreviations. Mass. Mass, of course, the base unit is the kilogram. Some people might think it should be the gram, but it's not. It is the kilogram. The base unit of length, you are also familiar with, the meter. Time is measured in seconds. Temperature, the base unit is Kelvin. Electrical current is abbreviated with an A, and it is an ampere. Amount of substance, this one you know as well, is the mole, abbreviated MOL. And how bright is something? We measure that in candle power or candela. That's not the abbreviation. Let's see, I don't use this very often. I believe it's CD. You may want to check that out yourself. So we can take those base units. Every other measurement that you can imagine is made up of these base units. For example, a Pascal that we use to measure pressure, and often we do things like kPa for kilopascals, and you probably remember that standard pressure in kilopascals is 101.3 plus a little bit more. Standard pressure. Well, we could write this Pascal in base units, and the base units for the Pascal are kilogram per meter per second squared, or sometimes you might see it written like this, kilogram meter per second squared. That is a derived unit. And so other derived units that you're familiar with are things like area, length times width, gives us things like centimeters squared, or volume, length times width times height, gives us things like meters cubed. If I was going to keep that in base units, I guess I could do that. Density could be things like kilogram per meter cubed, although that's not a very common unit. Usually we see things like grams per centimeter cubed or kilograms per decimeter cubed. Derived units. And be sure you know these metric prefixes that we put on base units or other units, derived units, to determine, to make bigger units or smaller units so things are more convenient. And so capital M is mega, and that means 1 million things. So like mega meter would be capital M, little m, and it would be 1 million meters. More familiar to us is the kilometer, lowercase k, which means 1,000. And so when we see kilometer, you're much more familiar with kilometers, 1,000 meters. Centi, with a little c, you know that means 10 to the negative 1, or 1/100th. And so we know that a centimeter is something, a little skinnier than the width of your little finger, kind of a distance. Millimeter. Milli is 1 times 10 to the negative 3, 1,000th, and you're familiar with things like the millimeter. Micro. You need this symbol, 10 to the negative 6, or 1 million. So when you see micrometer or microliter, you know you're talking about 1/1,000,000th of that SI unit. Determination of accuracy and precision. Now, the first thing I want to mention here is you should know the names of all these instruments. You know, these graduated cylinders, these are volumetric pipettes, this is a burette, Erlenmeyer flask, and beaker. But the first thing I want to mention are here with the graduated cylinders. And what you would see, if you could see the graduations on those, you would see that the graduations here are down to the 10th of a milliliter, and that means you can make an estimate to the closest 100th of a milliliter with this instrument. And the graduations on the larger graduated cylinder are to the closest milliliter, so you can make an estimate to the closest 10th of a milliliter. So as you are measuring with these two instruments, sometimes, let's say you're measuring with this 100 milliliter graduated cylinder, its precision is lower than the precision of the 10 milliliter graduated cylinder. Now, what do we mean by that? We mean by that if you have a measurement that you're trying to target, sometimes you're going to be a little bit above that or a little bit below that measurement. So if this is our target, we're going to be a little bit below or a little bit above this measurement. Now, that consistency of being close to our value that we're shooting for, that consistency is known as precision. And if you're using this graduated cylinder and you're shooting for the same target, because it is a more precise graduated cylinder, you're going to be much closer to your target. You're still going to be a little above or a little below, but you're going to be much closer because this instrument measures more precisely. Now, this instrument, the volumetric pipette, is quite precise, usually to the closest 0.01 or even 0.001 milliliter, or it depends on the pipette. Some are much more precise than that. So I guess I shouldn't label that entire group with that precision. The burettes we use in class, we can usually make an estimate out to the closest 1/100th of a milliliter. But things like beakers and Erlenmeyer flasks, their precision are usually more like plus or minus 5 or 10 milliliters. Much less precise. So keep that in mind as you're looking at precision and accuracy. Precision is how close and how consistent you can be at making a measurement. Now, we indicate an instrument's or a measurement's precision when we write the measurement. So a measurement, when we write it, like let's say we were measuring 9.0 milliliters, we've indicated that this is a measurement, and this is the number of milliliters. This is the unit, of course. So those are the first two things we want to look at in a measurement. And the third thing we want to consider in a measurement is how precise that measurement is. And that precision is indicated by the number of significant digits. The whole reason we consider significant digits is to keep track of how precise the instruments were that made the measurements. Now, accuracy is percent error. How close are we to some accepted values? So if you're doing analytical chemistry and you want to make accurate measurements, and of course you must, you calibrate your instrument and you see how close it is to a standard that you know the concentration or the measurement for. And how close your instrument comes to that standard is its percent error, and that's one way we measure accuracy. This whole idea of the precision of an instrument is very important when we consider how we handle calculations of significant figures. And there's rules that count for addition and subtraction, and there are rules that count for multiplication and division. But it's all tied back to how precise was the instrument that I used to make this measurement. So let's say that I'm looking at a map on my computer, and I make an estimate based on the scale on my map that the distance between 2 points is 1,000 meters. And then I zoom in to a more precise level, and I make a measurement, and it is 100 meters. Now, the digit that is uncertain in the first measurement is this digit. Now, by that I mean this measurement could be somewhere between 500 and 1,500 meters, because this digit is where we made an estimate. This digit is our uncertain digit. Here, the uncertain digit in the second measurement is in this place. When we add these together, we don't go past that first uncertain digit. So, when we add these together, I'm going to add one, yeah, I can add this. There we go. Now it looks like 1,100 meters, but because we don't know with any degree of precision what this first measurement was, we really can't say that now our total distance is 1,100 meters. We have to round it to this place. So I'm looking at this number. It's less than 5, so I'm going to round this off to 1,000 meters. Now that's how the rule for addition and subtraction works. You always look for the least significant measurement, and you don't go past that digit that tells you how precise your instrument was. Multiplication and division use a slightly different rule. The rule for multiplication and division is if you have 1.53 and you multiply that by, and let's say that's centimeters, and you multiply that by 2 centimeters, you're going to get 3.06 centimeters squared. But the rule is this: we are looking at instruments here that indicate different precisions. This second instrument doesn't look as precise. It actually only measures to the closest centimeter. So our answer should not be any more precise than the closest centimeter. So the rule is you look for the number in your problem with the fewest number of sig figs, and that's the number of sig figs you put in your answer. So we're going to round it off to this place. This is less than 5, so I'm going to round this to 3 centimeters squared. That is the area, and that's the right number of sig figs. Now, a common problem students encounter with this is if you have a multi-step problem where you start with this and you calculate this and you take that number and you calculate this and you get clear down here to the end. How do you avoid having rounding errors? You don't round to the right number of sig figs until you get here to the end of your multi-step problem. Do not round to the number of sig figs as you constantly move through the problem. Take care of that at the very end, and that will eliminate rounding errors in the middle of the problem. Dimensional analysis is your friend. Your units will always lead you to the correct answer if you let them. So you just have to be clever about it sometimes. Remember, density is some kind of mass divided by some kind of volume. And let's say you're given a problem where you are asked to find the mass of an object when you're given its density. Well, remember, density is going to be in some kind of unit like gram divided by centimeters cubed. You're given the volume. Volume is going to probably be in centimeters cubed, or at least you'll need to get those into the same unit. But notice when we multiply these together, these factor to 1. And so the unit you're left with is mass. So that is what I mean by dimensional analysis. Or if you're making a conversion from 1.15 centimeters and you want to convert to millimeters, well, we do that with unit conversion or dimensional analysis. And I want centimeters to cancel out, so I'm going to put them on the bottom here. Centimeters are going to cancel out. Now, 1 centimeter, that's bigger than a millimeter, so one big thing has several little things. 1 centimeter is 10 millimeters, and so this becomes 11.5 millimeters. Dimensional analysis. The units need to be accounted for. You really are not going to have to focus on Fahrenheit temperature scale, but you should know things on the Celsius and Kelvin temperature scale. For example, you should know what is significant about the temperature 0 degrees Celsius or 100 degrees Celsius. Get those written in the right place here. Let's see. I'm going to write 0 degrees Celsius. You should know what's significant about those two temperatures, and you should be able to convert Celsius to Kelvin. Remember, all you have to do is add 273. So 373 Kelvin is the same as 100 degrees Celsius. And the same thing as 0 degrees Celsius is 273 Kelvin. Of course, remember the necessity of Kelvin. We usually use it for gas laws and some thermodynamic problems. We have to have our units in Kelvin. And the reason is Kelvin has no negative temperatures. And if you take 20 Kelvin and you double it to 40 Kelvin, you indeed have doubled the temperature. But if you take 0 degrees Celsius and you double the temperature, that's going to be, that's a little trickier, isn't it? How do you double 0 degrees Celsius? Well, it's really just double this number, 273 times 2. So, a few things about Kelvin and Celsius temperatures. I think we're going to just kind of skim over this. I'll let you look at that in your book or contact somebody if you have questions on calculations with density. Understanding the classification scheme of matter, be sure you consider this for a moment. that of all the types of matter that exist out there, we can classify them into one of these two groups. If I can spell them. Homogeneous and heterogeneous. Now, homogeneous simply means it's the same composition throughout. And of homogeneous matter, we have things that are solutions that have the same composition throughout the solution. Light will pass through a solution and things like that. And we have pure substances. Now, pure substances, of course, are things like elements and compounds. Now, you may want to read through the section of your book that focuses on how do we separate these kinds of mixtures. How do we separate solutions, the components of a solution, and how do we separate heterogeneous mixtures? Well, a lot of heterogeneous mixtures, we can do things like filter, or we can do things like chromatography. To separate them, and there are a few other things mentioned in your book. Solutions we can often separate with processes like distillation or even evaporation. So if you have a solution and you have a beaker with salt water in it, I'm going to say NaCl and water. How do we get the salt out? How do we just get the salt separated so we have just pure salt? I mean, people have been doing this for years, right? How do we get salt separated from the water? Well, that process you usually just call evaporation. You evaporate all the water away and leave the salt behind. So separation techniques can be very simple, or they can be quite complicated. So as we go through the year looking at labs, be sure you note these separation techniques that we're going to be using.